Hello, everyone. Today, Mr. Tallman here. Today, we're going to be talking about Lesson 7 practice problems from Unit 6. We're going to be doing number 1, 4, 5, and 6 on pages 64 to 67. Okay, so let's go ahead and start with this first one. We're basically going to be putting on a musical production at a theater, and we can tell how many tickets we're going to sell based upon this little expression right here, which basically says the higher the ticket price, the less tickets we're going to sell. Okay, so we're going to use this expression to fill out this table when we talk about number of tickets sold. Okay, so complete the table to find out how many tickets the theater expects to sell and what revenues it expects to receive at the given ticket prices. Okay, now revenues just means how much money we're going to make by selling these tickets. So for instance, if I sold one ticket at $5, I'd make $5. If I sold 10 tickets when they cost $5, I'd make $50. Okay, so we'll come back to that later. But let's go ahead and fill out this information first. Okay, so the first thing I'm going to do is input this right here. So 8 times 5 is 40, and 400 minus 40 is 360. Okay, so we're going to do the same thing here. We're going to input 10 up here. So 8 times 10 right here is 80. 40 minus 80 is 320. And then we're going to keep on going all the way down this list. We're just going to continue to input these values. So I'm going to use a calculator though for this one. For 8 times 15, that's 120 minus 400, that's 280 tickets. 20, that's 160, 240 tickets. 3, so 30 times 8, that's 240 minus 400, 160 tickets. And I can't do 45 in my head, so I'm going to have to do it on my calculator. So I'm taking out my little phone calculator and I'm going 45 times 8, and I'm subtracting that from 400. So 45 times 8, that equals 360. So 400 minus 360, well, that's just 40. We're selling less and less tickets. Okay, finally, I know that 500 times, or 50 times 8 is 400. So 400 minus 400 is 0. So the easiest one to start on here is right here. If I sold 0 tickets, I must have made $0. Right? So that's really easy. Right? Now, if I sold 40 tickets and each ticket cost $45, well, that's just 45 times 40. Okay, so 45 times 40, that's 1,800. And we're going to do the same thing all the way up here. We're just going to be multiplying these two together. Okay, just to see what they all equal. So I'm just creating an equation right here. Pretty easy. 30 times 160, 4,800. 20 times 240, 4,800. 15 times 280, 4,200. 10 times 320, 3,200, and 5 times 360. That's 1,800. Okay, now we can tell by looking at this, the values are going up and then they're going back down. So whatever the equation that we come up with down here must be quadratic, right? Let's go ahead and do this equation first though. In order to get these numbers right here, all we did was use this expression. So if this is P, the number of tickets sold is 400 minus 8P. And to get this equation, all we have to do is just remember what we did up here. We took this number and multiplied it by this number. Now that's pretty easy. We're going to take this and multiply it by, well, not just the 400, this entire thing, right? Because we had to do this entire thing to get each one of these numbers. Okay? So in order to get this, I'm going to write this entire thing down. P times 400 minus 8. And if I distribute that, notice this is P times 8P, or negative 8P. That becomes P squared. So that's how I know it's quadratic. And this tells me, right? It goes up, and then it starts coming back down. All right. For which ticket price will the theater earn no revenue? Obviously 50, because we sold 0 tickets. $50, we sold 0 tickets and made 0 money. At which ticket price should the theater sell the tickets if it must earn at least 30 or 3,200 in revenue to break even on the musical production? Well, we just need to find out where revenue is 3,200. Well, right here. So $10. That's in revenue. Oops. Is 3,200 from our table right there. Okay. All right. That's the end of number 1. Let's go ahead and move on to number 4. Whoop. All right, let's zoom in here. All right. Write an equation to represent the relationship between a step number n and the number of small squares y. Okay, so these are my small squares, and these are my step numbers. Okay, remember, whenever we're looking at these, we're looking for a quadratic relationship, which means we're looking for something that is squared, right? Or to the second power. That's like how I know an equation is quadratic, right? It has that little 2 up there, and that means squared, like x squared, or x to the second power. And the reason we say that is because we're looking for perfect squares when we see this. Now here I see 2 perfect squares. I see one down here and one up here. Okay, let's see if that pattern continues. Here's a perfect square, 4 by 4. And here's another perfect square. Or 2 by 2, 2 by 2. Oh, same thing here. There's a perfect square. Here's the first one. Here's my second one. Okay, notice the side lengths on these. They're 1 by 1, 2 by 2, 3 by 3. That coincides with the step number. So if I want to say how many small squares there are, so this is the number of small squares, I can say it's whatever this thing is, 2 squared, 3 squared. So my step number, which is n, so n squared, except for there's 2 of them. So I could say n squared plus n squared. But if I'm adding the same thing together twice, another way to write that is to say y equals 2 times n squared, because there's 2 of them, right? Either way would work. It's up to you on how you want to write it. Okay, is the relationship between the step number and the number of small squares quadratic? Yes, and we know that because of this right here. Yes. First off, there are squares, right? There's perfect squares in each one of these. And they're getting progressively larger with relationship to the step number. But the equation has this little to the second power up there. Yes. The equation has a degree of 2, which means that the biggest exponent we can find is this number 2 right here. An exponent, all these little numbers up here. If there was like a 5 up here, we would say that's the degree of 5. But we're just going to say it has a degree of 2. That means it's quadratic. Okay, that's it with number 4. Let's go ahead and move on to number 5. All right. Take a look at this right here. This says technology required. That means you're probably going to have to use Desmos or some kind of online calculator. Let's read the explanation, the narrative. A small marshmallow is launched straight up in the air with a slingshot. Pew! I like that. That sounds like fun. The function h given by the equation h of t equals 5 plus 20t minus 5t squared describes the height of the marshmallow in meters as a function of time in seconds since it was launched. So this tells me how high it is, and those t's tells me how long since I launched it, right? 1 second, 2 seconds, 3 seconds, 4 seconds, etc. Okay, so using graphing technology, or use graphing technology to graph the function h. All right, all I'm going to do is plug that into Desmos. And you can see I've done that right here. Okay, so you can see the equation. If this thing moves, there we go. See the equation right there? And this is the flight pattern of my marshmallow. Okay, so we're going to find some interesting information about this by looking at this graph. All right, I'll go ahead and move that out of the way. Okay, about when does the marshmallow reach its maximum height? Well, you can see right here, that's its maximum height, and it gets there after 2 seconds. So the answer to B, oops, is 2 seconds, about 2 seconds. You don't need to be exact. About how long does it take before the marshmallow hits the ground? Well, if this is my marshmallow, it hits the ground right here, a little bit more than 4 seconds, right? So we don't need to be exact. It's asking us, it says about, right? Which means like about how long, I'd say it's about 4 seconds. And what domain makes sense for the function h in this situation? Remember, domain, range. Okay, and I always do this because when we look at graphs, we go x, y. Okay, so domain is this way. So we're trying to say what are the possible values of us launching this marshmallow. If I look at the graph, right, this says like negative 0.236, but this is time, right? How can we be backwards in time? We didn't launch this sucker until we were at 0. That's when we started counting, right? And we were already at 5, I don't know, whatever that was, feet maybe? Or no, meters high in the air when we launched it, right? So we can't really go back in time. So in this case, what makes sense is that we start at 0 and go until the marshmallow hits the ground, right? This thing will go down and down and down forever, but it hits the ground right here, so that's kind of when it stops. This is just the equation, right? Graphed in Desmos. So mathematically, the equation looks like that. But in real life, we launched it up here at 0 seconds, and it stopped falling at 4.236 seconds. So that's our domain. That's our domain. That's our range, or our domain of time from 0 all the way over to 4.236. So over here, we're going to go domain is from 0, and we can equal 0. Remember, t is our variable, right? So if I draw my graph, this was t, and this was h of t, instead of x and y. That's how our graph looked. And we landed at 4.236. Now, if you just said 4, that's fine too, because it's like about approximate, right? But what you need to do is you need to click on that little spot where it hits the ground, and it'll show you the actual coordinate, the point on it. Okay, hope this helped. If you have any more questions, please email me or your teacher, and we'll get it cleared up for you. See you next time.